Derivation of velocity on a string. This is mechanical wave. Okay, we've got a string here, and the string is experiencing a force that's moving in this direction with a velocity v, and hence there's a tension here. There's tension, and there's another tension here. If we pick 2 points, we call that point number 1 and point number 2. And so what we're going to have is a x coordinate for that in time t, and x plus delta x in time t plus delta t. So we're going to put that here. Point 1 has got at x at a time t, and point 2 at x plus delta x at a time t plus delta t. And if we take a distance here, the distance between these 2 points is dx. And what we're going to do is look at that point here and enlarge it. And then we're going to work out forces that is causing that point to rise up. So if we circle this point and enlarge it, if we enlarge this point, and we get this. So that point here is this bit here, and this bit here is that bit. So we have a velocity in the y direction because this string is going up. From there is going up. So we have a velocity in the y direction and a velocity in the x direction. And there's an angle theta here. So if we take that height here, we call it delta y, and that distance is delta x, the distance traveled. So v, velocity, is change in displacement over change in time. So we can say dx over dt. Therefore, the x will be equal to v dt. So if we multiply both sides by dt. Now we've set the velocity in the x direction, we can write velocity in the y direction, and that will be dy over dt. And therefore, dy equals vy dt. If we remember SOHCAHTOA, if we can apply SOHCAHTOA here, we can find dy over dx. dy over dx is opposite over adjacent. Opposite over adjacent is tan theta. And because of that, we can now say dy dx equals tan theta. We can also say that dy over dx equals vy dt over v dt, and the t cancel out. Therefore, we can say dy over dx equals vy over v. Therefore, we can say tan theta equals vy over v. And we can write vy as the subject, and that equals v tan theta. So velocity in the y direction equals v tan theta. Now we're going to look at tension here and the force in the y direction that is pushing this up, and the string will be experiencing a force here, and that force in the y direction. So there is a tension in this direction. There's a tension, and that's the hypotenuse, and the opposite will be here, and that will be Fy. And so writing the sine of an angle theta will be opposite, which is Fy over tension, and Fy will be equal to T sine theta. So do remember the Fy is the force in this direction. So that's Fy. And applying sine of an angle theta will be opposite over hypotenuse, and hypotenuse is the tension, Fy over T. We have the mass of the string divided by its length, L, and we call that mu, and the unit for mu is kilogram per meter. So now we're going to look at impulse. Impulse is force times time, and that also equals to change in momentum. P is momentum. Impulse I equals to force in the y direction times time, but the time is a small change in time, so we call that dt, and that equals to the change in mass times velocity, because momentum is mass times velocity. I can replace the force with t sine theta and then the t. So that's the t here, and Fy is t sine theta. And that equals to v for y times dm. The m is the change in mass, and I just took the v and put it out here, and then I've changed in mass, and I replaced this theta with a small d. So this v is vy, and that delta is this d, and that's the mass. But I know what mass is. Mass is L times mu, but L is x. So I can rewrite that. So that would be Vy mu dx. Remember that L equals x. So L equals x, but I'm replacing the m with L times mu. So L times mu here, and I'm replacing the L with x. So that's how I got my mu dx, which is the mass. So just to remember that m equals mu times L, which then equals mu times x. So if I have change in m, which I call the m, and then I can have the mu x, and the mu x is basically what I wrote here as mu dx, and that's what I put here, and that's what I put here. Mu dx is that. So to continue, I have t sine theta dt equals, now v is basically here, this is vy, so I'm going to replace vy with v tan theta, and so that would be equal to v tan theta, and then I'll have mu dx. But for a small angle where sine theta would be approximately equal to theta, and tan theta will be approximately equal to theta, I'm going to have t theta dt equals to v theta mu dx. But theta will cancel out. Then I'm going to get t dt equals v mu dx. So I get t dt equals v mu dx. If I divide both sides by the t, then we get t equals v mu dx dt. But the x dt is v. So we have t equals v mu v. V times v is v squared. T equals mu v squared. Therefore, v squared equals t over mu. Now we can write v equals square root t over mu. But you can also replace mu with m over L, so v can be written as root T over M over L. And that would be equal to root T L over M. That's V. So the equation that is written all the time for speed or velocity in a string is going to be root tension over mu. Or you can write as speed or velocity equals to square root tension times length over mass.